We now turn to the second of the projections commonly used in aviation, the Lambert's conical conformal chart. The first question is, why do we use it? After all, we have the Mercator. We have seen that the Mercator projection has many powerful properties, but it does have two limitations. Firstly, great circles are not projected as straight lines. Secondly, the chart is not constant scale. Indeed, scale changes quite rapidly on a Mercator chart. Navigators wish to maintain rumline tracks for the first 400 years or so of the life of the Mercator chart, because they were steering by compass, and therefore needed to have a constant track direction. However, that situation started to change from about 1960 onwards, when automatic computing became available. It is possible to calculate a constantly changing desired great circle track direction by spherical trigonometry formulae, and the computers built into INS, IRS, FMS and GPS do this continuously as a matter of course. Therefore, if the aircraft is going to be steered along a great circle, it will be helpful to have a chart on which a great circle is a straight line. Otherwise, the aircraft will appear to go off track in the middle of the leg, then recover back to track again. Also, if the scale were to remain constant on a chart, we could measure distances with a ruler instead of having to use a pair of dividers and then having to open the dividers to different distances at different latitudes. For aviation, it is useful to be able to measure with a ruler. Most aircraft do not have a large plotting table like a ship. The basis of the Lambert chart is the simple conical projection. However, the simple perspective projection has some limitations, the most important being that it is not orthomorphic. A German mathematician called Johann Heinrich Lambert made some modifications to the basic conic in 1777. The result is the orthomorphic, near constant scale Lambert's conic conformal chart. The approach taken in the first part of this lesson will be firstly to derive some of the properties of the simple conic projection. Some of these, particularly the chart convergence, are also found in the Lambert projection. We will next examine why Lambert made his changes and what effect they had. This will give us the properties of the Lambert projection. First, let's remind ourselves of how the basic conic is produced. We have a reduced Earth at the same scale as the chart we wish to project. The light is in the centre of the Earth for this projection. A cone touches the Earth at a particular parallel of latitude. The graticule is projected. The cone is developed. That simply means that it is laid flat. The result is a circle with a sector missing. What we see here represents the northern hemisphere of the whole Earth. However, for a typical chart, we would need to see only a small area, perhaps one country or one continent. So we would take a small part of the projection, represented by the red square here, and expand it to a suitable scale. This conical projection forms the basis of the Lambert's chart. You are already familiar with the Jeppesen ED6, which is a Lambert's, and the same projection is also used by the CAA for the basic UK half-million topographical chart. The parallel of latitude at which the cone touches the reduced Earth is called the parallel of tangency, or the parallel of origin. In this example, our parallel of tangency is 45 degrees north. When the cone is flattened, 360 degrees of longitude are represented by a sector of a circle of 255 degrees. The size of the sector is determined by the parallel of latitude chosen to be the parallel of tangency. If a higher latitude is chosen, the sector will comprise a larger angle. Look at this diagram. Again, we have chosen a parallel of tangency of 45 degrees as an example. You can see that if we take this parallel as the base of a triangle formed by the cross-section of the cone, we get an isosceles triangle with the angle at the apex being 90 degrees. You can see why. If the latitude is 45 degrees, the angles at the base are 45 degrees. The internal angles of a triangle have to add up to 180 degrees. Two lots of 45 come to 90, which leaves 90 degrees as the angle at the top. In fact, there is a general rule. The angle at the apex is always twice the parallel of tangency. If we chose a parallel of tangency of 30 degrees, the apex angle would be 60. If we chose a parallel of tangency of 60 degrees, the apex angle would be 120. And the ultimate case is at the pole, where the parallel of tangency is 90. The result is an angle of 180 degrees, in other words, a flat sheet. We shall meet this again in the polar stereographic projection. The apex angle is known as the angle of the cone. It determines the angle of the arc of the sector formed by laying the cone flat. The relationship of the sector to the original 360 degrees of longitude is determined by the sign of the parallel of origin. The equation is that the arc of the sector equals the change of longitude times the sign of the parallel of origin. We have 360 degrees of longitude change between 180 east and 180 west. We have a parallel of origin of 45 degrees in this example. If you use a calculator, you'll find that this comes to 255 degrees. So, 360 degrees of Earth longitude is represented by an angle of inclination on the chart of 255 degrees. This gives a general relationship. In this example, a change of longitude of 100 degrees is represented on the chart by an angle of inclination of the meridians of 100 times the sine of 45 degrees. Sine 45 is 0.7071. So the angle of inclination on the chart is 70.71. In this example, a change of longitude of 10 degrees on the Earth is represented by an angle of inclination of the meridians on the chart of 7.071 degrees. The angle of inclination on the chart is more usually called the chart convergence. This gives us the general formula that the chart convergence equals the change of longitude times the sign of the parallel of origin. The sign of the parallel of origin is often called the constant of the cone and is represented by the symbol little n. Just to remind you, we're still dealing with a simple conic projection here. We haven't yet gone on to Lambert's changes. Now we're going to look at how scale changes. On the simple conic projection, the scale is correct at the parallel of tangency. The paper touches the reduced Earth at this point. However, it expands away from this point rather rapidly. Lambert modified the simple conic cone in order to reduce the rate of scale change. Instead of doing this, he made his cone go inside the Earth's surface. It now touches at two separate parallels, and the scale is correct at both of these. It reduces inside them and expands outside. This gives a pattern like this. The parallel of tangency on the old simple conic is now called the parallel of origin. And the two parallels where the cone touches the reduced earth are called the standard parallels. Note that, as we said earlier, the scale is correct at the standard parallels. In this area, it is expanding away from them. And in this area, it is contracting. The scale becomes least, or if you prefer, is most contracted, at the parallel of origin. This has evened out the scale error across the whole of the chart, and made it more of a constant scale chart. If we divide the change of latitude over our Lambert's chart into sixths, like this, this will even out the scale distortion over the whole chart. The scale contraction here, on the parallel of origin, will be the same percentage scale expansion as here, at the top and bottom of the chart.